Okay, I'll speak about the ENDA-INR, which you just hear, and a little bit about ENDA-64 in mountain level. So some issues can be repeated again. Работает. Ага. Okay, just to remind you that this project was proposed by us in 2009 or 8. It is a so-called PRISMA project because hadrons are the main component of the hadronic shower and air shower, of course. And so, first of all, we need to measure hadrons, not secondary particles as electrons and gamma quanta, and the muons also. And the idea is that when primary cosmic ray interact, produce a shower, hadrons reach high energy hadrons, reach observation level, produce evaporation neutrons in the surrounding matter, in ground and soil and the building, if it is inside the building. And these secondary neutrons thermalized and can be captured inside the detectors, like this, we were shown before. And I should emphasize that these neutrons is not cascade neutrons, because some simulations were published when people tried to calculate neutrons with Corsica, high energy neutrons. It is not, they are very small amount in addition to this evaporation neutrons produced in the ground and thermalized in ground, because air is not a good thermalizer. And this is the first array of such type was a prototype of this. It was multicom, and then this is very small array of 3 detectors. It was proposed to make such detector in Baksan neutrino station, and this oscillogram shows the idea of the experiment. This big pulse is shower pulses, and electrons and positons and so on, and then delayed with very big delay. This is 10 millisecond delay pulses, and it is interesting that instead of electrons which are measured as energy deposit in the detector, neutrons are calculated one by one because they are separated in time and can be separated very clear if you have a long windows for its counting. And then the proposal was accepted by LASO, and today you hear about ENDA detectors, which is situated here. It is use the same detectors, and we call it electron neutrons detectors because they can detect both electron and neutron component by one detector. It's very interesting. And now it looks like this. We have 64 detectors, which were shown before. And again, I can speak a little about this. This is our scintillator. It is a dispersed silicon scintillator. The diameter is 70 centimeter. It's put inside this water tank, and this is light collecting cone. And this is a photomultiplier, Beijing Hamamatsu, 4-inch diameter. And the aims of this detector and its properties shown here. as I said, it able to measure two EAS components on whole area of this of the array. Possibility to record hadronic component on whole array, and it allows us to recover primaries correctly. Measuring of EAS component allows us hadronic also exclude so-called coreless showers, hadronless showers, because I'll show it later. Okay. This I can speak, like I can skip because Kirill showed this. It is only two pictures for winter time and summertime. Very difficult because on the mountain level there are no snow. And this is an example of the big recent event. This is number of electrons in the detector. This is number of neutrons in the detectors. And you see that 122 neutrons were recorded in these 16 detectors. And this is a simulation showing the correlation between primary energy and number of produced neutrons, not recorded, it is produced neutrons inside the ring of 10 meters. It is close to the side of our array. So this was used. And you see this almost clear linear function. This is to emphasize this, it is the same, but divided by energy. So straight line. And our working range is above 1 PeV and higher, because for smaller array it is maybe only this region. For higher array, we can, of course, move in to the right. This is a plot showing the experimental between electron density, central density and neutron central density near the core in one detector. One detector measure electrons and neutrons. And again, you see the close to the linear function. And just to remind you, the spectrum has Kuzmichov told this morning that there is no explanation of this spectrum. I have put inverse question and say that this is just correct spectrum because Air-Shaw methods measure work correctly only about 10 to 16 electron volts. And this bump produce only the electromagnetic component. Not in hadrons, and you will see it later on the next slide. This is our work published 5 years ago for array here in MEFI. It is a Prisma 32, and this is data measured in other experiment, and these black points the spectrum recovered from neutrons. And we see this bump coincides with the appearance of hadrons in these points. It's confirmed that the bump is not astrophysical origin. It is methodical origin. And all the also data measured at high altitude. In Yanbanjing, we have only 4 detector, and this is also spectrum recovered from neutrons, which is slope was close to 1.7. Okay. Also, I can show you the spectrum measured for high energy hadrons in Cascada in 1901 in Hamburg conference, and it was It is simulation and sorry, this is experiment and this simulation. This might be the last time when people simulated with and without the knee. And if you look carefully, you will see that measured spectrum 2.0 and 1.9 correspond to their calculations without the knee. Maybe this is the reason that this paper was never published, only on the conference. This is spectrum measured now in Prisma ENR. It is also has no knee. To see it more correctly, I multiplied it to n is power n to 1.73, and you see it is in this region of energy, approximately from 3 to 30 PeV, no change slope in address, no knee. So my summary is Prisma project was realized in 2019 as ENDA-INR at high altitude. Currently, we have running 4 clusters in Dow Chunk, and our proposal was to make 400 such detectors, but it is maybe in the future. And one is a small prototype of one cluster in Moscow, and measurement of 2 different at 2 different altitudes allows us to compare results and understand the altitude influence. It exists because the slope is different for newtons to this, but it's not reconstructed. When reconstructed, it will be, I hope, the same. And preliminary results obtained at sea level are in agreement with previous measurement with Prisma 31 and Prisma Yang-Banjing. And the Newton number spectrum at sea level has no knee, and its power index 1.7, 1.75, very close to the spectrum energy distribution below 1 PeV. Thank you.